Hey everyone, today's video is going to be a little experimental, I guess, because we are going to explore the workflow of coding a convolutional neural network using PyTorch, but the catch is, instead of using the popular datasets that you often come across in these kinds of tutorials, I wanted to show you a different approach. Many tutorials provide code templates using datasets like MNIST, like the Fashion MNIST, which is the most recent one, like the CIFAR10, which are totally fine. They're excellent choices. But the thing is, in my opinion, they can be quite overused for these kinds of videos. So I wanted to give you like a different perspective on the matter. So that's why I decided to use a different dataset that I found online called the LC25000 lung and colon histopathological image dataset. I know it's a huge name. So as I mentioned before, and also as the name suggests, um, it has 25,000 color images divided into 5 classes, each containing 5,000 images. So it's quite balanced. These images capture histopathological samples of lung and colon tissues. So for this video specifically, I encourage you to follow along and use this dataset. I'm gonna put everything in the description, the link, the references and such. However, I want to emphasize that the main goal here is to give you a glimpse of the workflow on coding your own CNN. So I believe it's kind of an opportunity for you to, get creative and find unique data sets related to your own personal interests and also to build your own CNN from scratch. So um, coming back to the data set, as you can see, we have this long column image data set. As I said, it has 25,000 images. As you can see, the name for the Jupyter notebook I created is lung cancer because for this video specifically, I'm just gonna use the lung cancer related images and also for simplicity. So as you can see, I've already separated in the lung image sets folder, the testing folder and the training folder. If I'm not mistaken, there are 12,000, yeah, 12,000 JPEG files for training and 12,000 for testing. No, actually 3,000 for testing. Yeah, that's correct. So inside the training folder, we actually have the classes divided on themselves, as I said before. We have the long ACA, the long N, and the long SEC. Me personally, I've not actually quite seen the images by themselves and try to find some relation in my head or something between the images so I can see that I can differentiate them. But as you can see, like the ACA images have this shade, and the N images have a brightish shade of pink, and the SEC come back to a more purple one. So I believe since this model is gonna take the three channels, it's gonna definitely gonna take this into consideration. So yeah, let's get going to code. I mean, I think I've kind of actually um, said enough about the dataset. So let's get going. First, we're going to import the libraries we're gonna use on this project. I have already put them here since it's not much of a problem, and most of them are used in most of the machine learning and deep learning um, tutorials, anyways. So the ones I'm gonna make personal comments about are actually the image folder, which is not quite used if you use the datasets from Torch Vision, such as CIFAR10 and the MNIST, and also make grid, which I'm gonna comment later on. So next we need to define a series of transformations um, to be applied to our image dataset. These transformations include resizing the images. So as you can see in the original images, we have a different shape of 700. As you can see, where's the shape? Where I can see the shape? Yeah, 768 pixels by 768 pixels. We want to shrink that into 150 by 150, so that's what we're gonna do. Transform. Yep. That compose. Okay. I actually have these details right here, so I'm just gonna paste them since it's much kind of easy to understand. So we are resizing the images, we are converting them into tensors, and we are also normalizing the images. So it gets easier for it to train to put in a similar scale. If you're wondering how I got these values, is actually when you use the transfers dot normalize, is gonna normalize between the channels. So it's not actually that difficult. You just have to calculate the means uh, related to each channel when you consider the batch, the whole data set. So we have these means and these standard deviations for our data set. So when we are gonna now load our training in testing datasets using the image folder, as I said before, class from Torch Vision. So the thing about Torch Vision image folder class is that it assumes that the images are organized into separate folders based on their respective classes, which is exactly what we have here. Lung cancer analysis, yeah. We have this lung image datasets. Let's get into training, and we have the classes, which are the folder. In each folder contains the images regarding this class. So in this case, the training images are stored in this train, and the testing images are stored here. So train dset equals to image folder, and the path that we're gonna use. And the same thing for the test dataset. And we also want to apply the transform that we just implemented. Yeah, so we have this image folder. Now the format of the image folder is important because the first element is gonna contain the tensors itself, or the images per se, and the second element is gonna contain the class. So I can already see that per order, my class 0 is gonna be the lung ACA, my class 1 is gonna be the lung N, and the class 2, the label 2 is gonna be the lung SEC. So, I mean, if you want to actually confirm it, so you just have to print the following. Yep, following classes are these. Okay, train the set of classes. Yeah, that's it. We have the lung ACA, the lung, and the lung SEC. So this is a good thing about the image folder, is that it has a lot of attributes that you can, make it easier to work with your data. So moving on, we set the batch size. So batch size equals to 8. Let's just try the validation size, which I'm gonna put like in 2000. The train size, which is gonna be equal to the length of the train set minus the val size. And what we're gonna do here is we're gonna do a random split to split the training data set into the desired proportions. So I'm gonna do this here. The train data and the val data are gonna be split between the train data set and the train size, val size, which you just declared before. So we have a length of train data equals to 10,000 and a length of validation data equals to 2,000. So now we need to create data loaders for our training and validation sets, which is quite common in any neural network that you are working with. These data loaders allow us to efficiently load the data in batches during training and validation processes. We pass then the training and validation datasets to the respective data loaders and specify additional parameters such as batch size, shuffling, the number of worker processes for data loading, which we are going to specifically turn to 0, so our machine handles the num workers. So train loader equals to data loader train data batch size equals to actually we don't have to declare because we already declared it up here. Shuffle equals true, That's it, and the num workers equals 0. Num workers equals 0. So you're also going to do the same thing for the validator loader. So we just need to copy this, the same configuration. Oops, val loader to the validator. Okay, that seems like it's fine, I guess. So to visualize a batch of images from the training dataset, we are going to actually use a auxiliary function. So def show batch, oops, batch, which is gonna take the data loader itself. So for images, labels, until fig x equals to vlt.subplots, which we imported. Let's say fig size equals to 16 by 12, I guess. Yeah, seems fine. X dot set xticks. Okay. Oops. Okay, we are also going to do the y sticks. And last but not least, actually the most important one, we're going to show the images. So we're going to use the make grid, which I said I would explain. So it's gonna take the images, then in row, which is gonna basically be the size, which we are going to display, and the permute, because the ax.imshow actually takes the order of the dimensions and then the channels. So we have to switch up the dimensions a little for it to read the way we want to. So break, that's basically it. Show, oops, show batch, and we're using like the train loader. And as you can see here, and as I mentioned before, we are normalizing the data. So first we have these kinds of data here for the lung ACA, but as I run this, you can see all these kinds of data that are not actually quite good looking, but that are actually better for the model to train on, because they are scaled on the they're normalized, and yeah, that's just better. So this function takes a data loader as an input and retrieves a batch of images and labels and displays them using matplotlib. So now it's time for the fun part. We're going to define our convolutional neural network using the nn.module class provided by PyTorch. So RCNN consists of multiple convolutional layers, ReLU activation layers, and max pooling layers, and it also incorporates fully connected layers at the end to perform, the classification we want to between the two classes. So the thing is, I already have this this network, because I'm gonna put the code in the description, in the inspiration code also. Um, it's not to be used as a template. You can also tweak it around. I actually recommend you to try to tune it, add layers, remove layers, change the hidden units, the hidden size and such, add activation functions, whatever you want, as long as you kind of follow some logic, I guess. But we have our neural network that takes the 3 channels, turns into 32 channels, and the thing is, as long as by the end it returns 3 classes, then you're good to go. So we defined our RCNN class, that's good. Once we have defined the model architecture, we set the device to the GPU if it is available, and otherwise we use the CPU. So this allows us to basically leverage the power of the GPU acceleration if it's accessible. So device equals torch dot device. So it's equals CUDA if torch dot CUDA dot is available. Okay. Else we are going to use the CPU. Seems fine. So as we just declared like the footprint of the CNN, we're gonna instantiate it. So model equals to CNN.to device, which we have a GPU. As you can see here, you're using CUDA because we have a GPU. So for training our model, we define the loss function now, just as any other model, and the optimizer, which are going to use the Atom optimizer to update the model's parameters. So the criterion is going to be an NDOS cross entropy loss because we have multiple classes that we want to predict. An optimizer is going to be an optim.atom model parameters. Let's set the learning rate for, I don't know, a minus 4, I guess. Seems fine. 0.000. Yeah, I don't know. He's not fine. Yeah, you can just put this. Or actually, 1. Yeah, that was actually it. Missed the 1. Okay, so next we set up a list to store the training losses for each epoch. This is not actually mandatory, but you know it's good when you have more complex problems and you want to analyze the model itself, how it's training and such. And now we enter the training loop, which will iterate for a specified number of epochs, which we're going to use, I don't know, 10 epochs or 20 epochs. And for each epoch, we iterate through the training data loader, and we also perform a forward pass through the model. We calculate the loss, we perform backpropagation, and update the model's parameters. So the epochs, actually, num epochs equals to 10. So for epoch in range num epochs, the running loss, which are gonna append and the losses on itself, is gonna start with 0, and then we're going to iterate over on the batches on itself. So images, labels, and enumerate. Oops, enumerate. Okay, the train loader, which is the loader we're going to train our data. So the images are going to be passed to this GPU. So images equals the images to device. You can see here that we are basically passing the batches one by one as we train to our GPU, to accelerate the process. So optimizer dot zero grad to make the gradients equal to 0, output equals to model dot images, which is gonna perform our forward propagation images. Okay. The loss is gonna be our criterion. Outputs, labels. Okay. Then we perform the backpropagation on the loss, and we take the step following our Atom optimizer. Seems okay. Now by the end of each of these ones, I'm gonna update the loss. So running loss is gonna be summed with the loss.item. Okay, and I'm gonna actually each, I don't know, 250. Actually, when we pass through a certain number of loops, we are gonna print the epoch we are in and the running loss. So we're going to print epoch, which is gonna be, actually I have this right here. Okay, oops, this one is better. Okay, this one, nice. So we're going to print our epoch out of the total number of epochs, the step we are in, and the running loss that we are in. And then we are going to turn this running loss to 0, so it doesn't accumulate. And by the end of each one of these for loops, we're going to append the losses, because it's basically doing it for an entire epoch. So if we have 10 epochs, we're gonna do this 10 times. After training, like, I think this is kind of good to go. I'm not gonna run it just yet because I actually want to see the how it's performing. So after training, we switch the model to the evaluation model using model.eval, and we evaluate its performance on the validation set. So we need to calculate the accuracy by comparing the predicted labels with the true labels, and then we print the result. So model.eval. I'm actually thinking on skipping this part because, as just I said, it's basically common in most of the cross entropy problems. So I'm just gonna do this. We have the coverage, we have the total. So for each image in the eval loader, we're basically gonna do the same step of training, but by the end, we're gonna basically compare the predicted values on our model, passing the validation data, and the actual labels and sum them to see how much was right in these predictions. And by the end of each for loop, actually of the for loops, I'm gonna print the accuracy on the validation set, which is gonna be correct over total times 100 and the percent sign. I think that's fine. So as I said, we have the losses here, which is a list. So we can use matplotlib to plot these losses, which, as I said, is not mandatory, but you know, for more complex problems is actually good practice. So X label is gonna be epoch. I actually don't like using double quotes. And plc.y label loss, plc.title. It's gonna be training loss, and by the end we're gonna show the plot on itself. So after we've done the validation accuracy, we are going to do the same thing on the test loader. The thing is, doing the same thing in the test loader in this problem specifically is actually the same as the validation set, because we use the validation set when we are still tuning our model, you know, finding the best hyperparameters, using, I don't know, Optuna, using randomized arXiv, which is actually you know, I recommend you guys do it on this project. But since we are not actually, we are just running the code all at once, it doesn't make much sense to separate the validation and the testing set, but you're doing anyways, so you can have like a feeling of what you might do when you're actually coding and you want to tune the hyperparameters on itself, and actually to see the performance on the validation as well as on the testing set. So I'm just gonna up the test loader. I'm gonna declare, which is equal data loader. Oops, data loader test dset, which you already imported. The batch size num workers equals 0. And I'm just gonna copy what I've had before, which is basically the same thing, except this time is for the testing set. So that basically concludes the code. Now let's run our training. We already ran to the losses. So yeah, we are using 10 epochs. I mean, you can kind of adjust it to whatever you want. Try, you know, picking bigger numbers, or you know, try to tweak the learning rate and such. Try to definitely try to take the CNN on itself, the architecture, like the, as I said, the comp2d, the activation functions, the pooling layers, the convolutional layers and such. And well, this is gonna be actually taking a while because it's running on each epoch, um, and CNNs take a lot of memory, and I don't have actually the quite of a super GPU. I have a RTX 2060 in a notebook, so we have this. It already completed like the first batch of the first epoch, 250 by yeah. It's gonna be basically take 5 steps in each epoch. Okay, so it's gonna be like 50 lines of output here. So when you're done, I'm actually gonna stop the recording here, and we're actually done. I am gonna go back and see the results with you. So see you guys in a minute. So we are back, and as you can see, we are actually still training our model. We are at the end of it, but as you can see, the loss is kind of hovering around this number 0.01 or such. So that might indicate that we are overfitting or that it doesn't, have anything more to, improve because either our architecture is limited or the learning rate it's too high. So you might want to tweak a little around a bit. Try tuning the learning rate, increasing the number of epochs when you do that, change the architecture and such. So yeah, by the end of it, we see that loss is equal to 0.0140. We already ran the cell. So yeah, that's basically it. We are now going to evaluate our model regarding the validation dataset. So as you can see, we are doing it in the same number of batches, which are the size of 8. Yeah, which are the batch size of length equals to 8, and it should return a value, I'd suppose higher than 90% because our model is quite good. So yeah, the accuracy on validation set was 97.2%, which is quite good. I mean, uh, out of 100 images, out of 1,000 images, it gets 972 right. And we see here the evolution of the loss. It's actually quite not working because I've actually kind of rerun this. But anyways, that's something that happens. Um, and it actually, as I said, it stayed low for quite a while. It's hovering about 0.014, 0.1095, and I think the problem is I actually appended it on the wrong position, but that's not important right now. You can check it out, see it later on, so you can figure it out. And for the last thing, we are gonna do the same to see the performance of our model regarding the testing dataset, which, as I commented earlier, is like the same approach as the validation set since we are not tuning our model anymore. So it should be like something close to the validation dataset. Out of 1,000 images, it's probably gonna get right 900 and 80, 970. So let's just wait a little while it's processing all the batches and testing the accuracy of the correct over the total number of images. So as I said, the accuracy on the test set was 97.46%, which was actually really close to the validation set. And that's basically it. I mean, we managed to train our model, which we produced from nothing on PyTorch, um, to basically learn the classes of a model regarding the lung cancer dataset. and we actually got a really good result. So that's basically to show you the potential that you have, not limiting yourself on, you know, basically the most famous datasets that are used, and using it on the datasets that you have the most interest in. And that concludes basically the code for this demonstration. We are basically demonstrating the process of training a CNN model for image classification using PyTorch on our own dataset, on our dataset that we have interested in our dataset that we just found online, in that we saw the potential to train and refine our skills, and the results achieved on both, and the validation in the testing sets are a testament to the model's ability to learn and to generalize from the provided data set. So yeah, I think that's it. I hope you enjoyed it. Thank you for your attention, and I hope you found this monologue informative. And as I said, just tweak it around a little on it. Try to tune it on yourself. Try to implement it on your own images, or in images that you have found on Kaggle. Um, as you can see, this notebook, this video specifically, it didn't focus too much on the theory because I already implemented it in a way that I imagined that you all had this knowledge on CNNs, and that's basically regarding when you are declaring the model in itself, like the class CNN itself. So you have to do the calculations right to uh, get this final result of 82,944, but you have to keep track of the cells because it all needs to add up in the final, so you can have this linear of this value by 1024 into 512 into three classes, which are the classes we are going to use. One thing you could do is actually, since I'm going to provide the link for this dataset, you could try to not only use the lung dataset, but also the colon one, which is actually in the same repository, in the same folder. So give it a go, and give it a go on other datasets as well. I hope you enjoyed it. I hope it was quite informative. So yeah, that's basically it for now. Thank you for your attention, and see you next time.